I'd just like to give you a quick demonstration here on the application of the sine squared wave to total system generator power. So what I've got here, this is a tool called Desmos. It's available just www.desmos.com. You can use it for free or you can create an account. It's a really useful tool for graphing waveforms. You do have to, if you decide to use it, you do have to go up here to the graph settings, and you'd want to change the units to degrees, and then you can set your scale to whatever you'd like. You can also zoom and pan around as well. So if I just visualize, and I've already set these up here, I'm just going to visualize a sine squared wave. And you can see that as we go through 180 and then 360 degrees of rotation, excuse me, of cycle rather, we end up with two full waveforms. That's exactly what we would expect to see if we were to contrast it with perhaps just a sine wave, sine of x. Okay, and you can see there, and I'm only showing the bottom half, or I should say the top half. I'm missing the bottom half of the sine wave if I had the view the way it was. So there's a sine wave in comparison with a sine squared wave. So we're only concerned with the sine squared wave now because I want to look at the effects of power and how exactly is it that the total power from a polyphase, a two-phase generator, the total average power ends up being a complete flat line. So you can see that the peak of this waveform here is just 1. So if I was to view a sine squared wave, and then I'm going to also turn on a sine squared wave that's phase shifted by 90 degrees. So the blue waveform is lagging the red waveform by 90 degrees. What you can see is that your peaks and your midpoints have a crossing. In fact, that crossing is right at exactly half of the peak value. But the cool thing about this, and this is representing, by the way, this is representing the power output from one phase versus the power output from the second phase of a two-phase generator. So if I was to turn on this third graph that I've created here, which is the sine squared x plus the sine squared x minus 90, I'm just going to add the red and the blue waveforms together, and there you are. You've got a green line that is flat, and it's representing a value of 1, or just simply it's hanging at the peak value. And so this just shows you that for two balanced loads on a two-phase generator, you end up with the total power being delivered from the machine being equal to the peak power for any of the total waveforms, as long as they're balanced. Now I'm going to turn off the sum and the phase shifted waveform, and instead we're now going to look at the three-phase machine, the output from the three-phase machine. So the power pulses, they're going to be separated by not 90 degrees but 120 degrees. Okay, so what I've got here now is I have three waveforms. They're separated by 120 degrees. I've got my peaks happening here. Now there's 120 degrees between each waveform. If I was to sum the blue plus the red plus the green waveform, this is representing the power from all three phases being delivered to identical loads. Remember, I mentioned in the video on three-phase generators that the total power of the machine ends up being, again, a flat line, but it's 1.5 times the peak power for any particular phase. So if I turn on my graph here that's showing sine squared x plus sine squared x minus 120 plus sine squared x minus 240, we see a flat line, and it's happening right up here at 1.5. So 1 being the peak, 1.5, so that's 1.5 times the peak value. So this is a neat tool, it's a useful tool, Desmos.com. I would encourage you to play around with it and get used to using it. It'll definitely help you visualize some of these waveforms that we're going to work with.